Hi everyone! Today we're going to study basic operations of Boolean algebra. The circuits in computers and other electronic devices have inputs, each of which is either a 0 or a 1, and produce outputs that are also zeros and ones. Circuits can be constructed using any basic element that has two different states. Such elements include switches that can be in either the on or the off position, and optical devices that can be either lit or unlit. The operation of a circuit is defined by a Boolean function that specifies the value of an output for each set of inputs. The first step in constructing a circuit is to represent its Boolean function by an expression built up using the basic operations of Boolean algebra. Boolean algebra provides the operations and the rules for working with a set whose elements are 0 and 1. Electronic and optical switches can be studied using this set and the rules of Boolean algebra. Let's go now to the basic operations of Boolean algebra. The three mostly used operations in Boolean algebra are complementation, the Boolean sum, and the Boolean product. Let's begin with the complementation. The complement of an element is denoted by a bar. 0 bar equals 1, 1 bar equals 0. This is now the Boolean sum. The Boolean sum, denoted by plus or by operation OR, has the following values. 1 plus 1 equals 1. 1 plus 0 equals 1. 0 plus 1 equals 1. 0 plus 0 equals 0. Here is the Boolean product. The Boolean product, denoted by a dot or by AND operation, has the following values. 1 times 1 equals 1. 1 times 0 equals 0. 0 times 1 equals 0. 0 times 0 equals 0. Let us extend our study with the Boolean XOR operator. The Boolean operator using the symbol called the XOR operator is defined by 1 XOR 1 equals 0. 1 XOR 0 equals 1. 0 XOR 1 equals 1. 0 XOR 0 equals 0. Let us see some examples. This is the first one. Find the value of 1 times 0 plus the complement of the quantity 0 plus 1. For our solution, let us copy the same problem down here, and then let us find the values of the operation. This 1 times 0 is 0, then plus the quantity 0 plus 1 is 1. Let us simplify this 1 bar, and that will be 0. 0 plus 0 is 0. This is the final answer. Example 2. Translate 1 times 0 plus the complement of the quantity 0 plus 1 equals 0 into a logical equivalence. For our solution, let us translate 1 into a t, 0 into f, Boolean sum into disjunction, Boolean product into a conjunction, complementation into negation. So for our answer, this 1 times 0 is now t and f, plus now becomes or. The complement of 0 plus 1, we write here not of the quantity f or t, is equivalent to 0 becomes f. This is the final answer. Example 3. Translate the logical equivalence t and t, or not f is equivalent to t, into an identity in Boolean algebra. For our solution, we're going to translate t into a 1, f into a 0, disjunction into a Boolean sum, conjunction into a Boolean product, negation into a complementation. For our answer, we will write here that t and t becomes 1 times 1, or becomes plus, the not f becomes 0 bar, the symbol of equivalence is now equal sign, and the t is changed into 1. This is the final answer. Today, we're going to study Boolean functions. Let us define Boolean function. Let B be a set with elements 0 and 1. A variable x is called a Boolean variable if it assumes values only from B. That is, if its only possible values are 0 and 1. Then B with power n equals x sub 1, x sub 2, x sub 3 up to x sub n, such that x sub I is an element of B, for I is between the values from 1 to n, is the set of all possible and tuples of zeros and ones. A function from b raised to n to b, denoted by this notation, f colon b raised to n arrow b, is called a Boolean function of degree n. Let us see example 1. The function capital F of xy equals x y bar. From the set of ordered pairs of Boolean variables to the set 0, 1 is a Boolean function of degree 2. To evaluate the function, we can do like this. First, let us copy our function down here, and let us write all the possible combination of the function given the combination of 0 and 1. So we have here 4 combinations: f11, f01, f10, f00. And from here, let us evaluate the values using the right side pattern. So the first number is for the x, the second number is for the y. So we have now 1 times 1 bar, and then let us evaluate 1 bar to be 0. 1 times 0 is equal to 0. The F01 we write here 0 times 1 bar. The 1 bar becomes 0. 0 times 0 is 0. F10. So we write 1 times 0 bar. 0 bar becomes 1. 1 times 1 is 1. This F00 now becomes 0 times 0 bar. 0 bar becomes 1. 0 times 1 is 0. So we are done with the values, which means F11 is 0, F01 is 0, F10 is 1, F00 is 0. This is now our answer. We can show another solution using truth tables. First, let us show the x and y columns with all the corresponding values of 1 and 0. And then, for the next column, we write the y bar, which means 1 becomes 0 here and the 0 becomes 1 respectively. Then, let us now evaluate our function, x times y bar. This is our x column, this is our y column. We're going to multiply the corresponding values. 1 times 0 is 0, 1 times 1 is 1, 0 times 0 is 0, 0 times 1 is 0. Please observe that our answer in this column is correspondingly the same with our solution in the first method. This is the final answer. Example 2. Find the values of the Boolean function represented by f x y z equals xy plus z bar. For our solution, we will do this using the truth table. First, let us write the columns for x, y, and z. Next column, we will do xy, x times y. So 1 times 1 is 1, 1 times 1 is 1, 1 times 0 is 0, and all the rest down here will be 0. Another column for z bar. We're going to complement the z. So 1 becomes 0 and 0 becomes 1 respectively. And on the last column, we can now evaluate our function, the xy plus z bar. So this is the xy column, this is the z bar column. We're going to add them. So 1 plus 0 is 1, 1 plus 1 is 1, 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 0, 0, 0 plus 1, 1, 0 plus 0, 0, 0 plus 1 is 1. This is our final answer. Today, we're going to study identities of Boolean algebra. There are many identities of Boolean algebra. Here are the most commonly used. The first one is the law of the double complement. And this is x double bar equals x. Idempotent laws. There are two parts. X plus x equals x. Another one is x times x equals x. Identity laws. The first part is x plus 0 equals x. Second part, x times 1 equals x. domination laws. First part is x plus 1 equals 1. Second part, x times 0 equals 0. Commutative laws. The first part is x plus y equals y plus x. Second part is xy equals yx. Next is associative laws. The first part is x plus the quantity y plus z equals the quantity x plus y, then plus z. Second part, x times the quantity y times z equals the quantity x times y, then times z. This is now the distributive laws. The first part, x plus yz equals the quantity x plus y times x plus z. Second part, x times the quantity y plus z equals xy plus xz. De Morgan's laws. The first part is the complement of xy equals x complement plus y complement. The second part is the complement of the quantity x plus y equals x complement times y complement. Absorption laws. The first part is x plus xy equals x. Second part, x times the quantity x plus y equals x. Next is the unit property. It says x plus x complement equals 1. And the zero property says x times x complement equals 0. Let us see this example. Translate the distributive law x plus yz equals the quantity x plus y times the quantity x plus z into a logical equivalence. For the solution to translate a Boolean identity into a logical equivalence, number 1, we will change Boolean variables x, y, and z into the propositional variables p, q, and r respectively. We change Boolean sum into a disjunction. We change Boolean product into a conjunction. So for our answer, we will write like this. The x becomes p, the plus becomes or. This y times z is now the quantity q and r. The equal sign now becomes the equivalence sign. Then x plus y becomes p or q. The multiplication here becomes and the x plus z is now p or r. This is our final answer. Today, we're going to study duality. Let us define dual. The dual of a Boolean expression is obtained by interchanging Boolean sums and Boolean products and interchanging zeros and ones. Let us see example 1. Find the dual of x times y plus 0. Remember that we should interchange Boolean sums and Boolean products. Also, interchange zeros and ones. For our answer, it will now be x. The multiplication here becomes plus, and the y plus 0 becomes y multiplied by 1. This is the final answer. Example 2. Find the dual of x complement times 1 plus the quantity y complement plus z. For our solution, we will interchange Boolean sums and Boolean products, also interchange zeros and ones. So the x complement times 1 becomes x complement plus 0. The plus here becomes multiplication, and this y complement plus z, we write now y complement times z. This is the final answer. Example 3. Construct an identity from the absorption law. X times the quantity x plus y equals x by taking duals. In here, we're going to interchange Boolean sums and Boolean products. So for our answer, we write x plus, so the x plus y here now becomes x times y equals x. This is the final answer. Today, we're going to study representation of Boolean functions. Any Boolean function can be represented by a Boolean sum of Boolean products of the variables and their complements using the three Boolean operators: this dot for Boolean product, the plus for Boolean sum, and the bar for the complement. Let us see this example. Find Boolean expressions that represent the functions f, x, y, z, and function g, x, y, z, which are given in the table. Let's begin with the function f. Looking at our column here, we can see that all the numbers are 0 except number 1. So our goal here is to find an expression to represent the function f, and that is an expression that has the value 1 when x equals z equals 1 and y equals 0, and value 0 otherwise. Such an expression can be formed by taking the Boolean product of x, the y complement, and z. As we can see, the x here is 1, the y is 0, and the z is 1. So the product we will write in here, and this is x times y complement times z. This is the function for f. Now the function g. In this column, we can see that all the numbers are 0 except for 2, which are numbers 1. To represent g, we need an expression that equals 1. In this first line, we can see that x equals y equals 1 and the z equals 0. While on this line, we can see that the x equals z equals 0 and the y equals 1. So we are going to form an expression with these values by taking the Boolean sum of two different Boolean products. So for our first line here, this will now be represented by x times y times z bar, then plus The second line, x bar times y times z bar. This is our final answer. Now let us define min term. A literal is a Boolean variable or its complement. A min term of the Boolean variables x sub 1, x sub 2, up to x sub n is a Boolean product y sub 1 times y sub 2 times up to y sub n, where y sub I equals x sub I, or y sub I equals the complement of x sub I. Hence, a min term is a product of n literals, with one literal for each variable. Let us see this example. Find a min term that equals 1 if x sub 1 equals x sub 3 equals 0, and x sub 2 equals x sub 4 equals x sub 5 equals 1, and equals 0 otherwise. For our solution, we're going to show the variables as a product that equals 1. It means let us begin with x sub 1. For our x sub 1, we will write here the complement of x sub 1. Since our x sub 1 here is 0, the complement is 1. So for the x sub 1, we write its complement, followed by the x sub 2. X sub 2 here is equal to 1, so we will just copy this as is. Then x sub 3. Note also that x sub 3 equals 0, so we will take the complement of x sub 3. So we write here x sub 3 bar. Then x sub 4, and that is equal to 1, we will just copy down here, followed by the last variable x sub 5. This is equal to 1 also, so we will just copy it in here. So x sub 1 complement times x sub 2 times x sub 3 complement times x sub 4 times x sub 5. This is the min term. This is our final answer. Today, we're going to study sum of products expansion. By taking Boolean sums of distinct min terms, we can build up a Boolean expression with a specified set of values. A Boolean sum of min terms has the value 1 when exactly one of the min terms in the sum has the value 1, while having the value 0 for all other combinations of values of the variables. Consequently, given a Boolean function, a Boolean sum of min terms can be formed that has the value 1 when this Boolean function has the value 1 and has the value 0 when the function has the value 0. The min terms in the Boolean sum correspond to those combinations of values for which the function has the value 1. The sum of min terms that represents the function is called the sum of products expansion, or the disjunctive normal form of the Boolean function. Let us see this example 1. Find the sum of products expansion of the function f of xy equals x bar plus y. To solve this, our goal is to convert the function into a sum of products of the variables or its complements using identities. Let us copy our function down here. For our step 1, we're going to show that each of these variables is a product of 1 and itself. So it will be x bar times 1, then plus this y times 1. This idea is coming from identity law that says x times 1 equals x. We have two products now. In our first product, this is x bar times 1. We can see that there is no variable y in the first product. We're going to introduce now a variable y to replace the number 1. Meanwhile, for the second product, y times 1, there is no variable x. We're going to replace the number 1 by an expression equivalent to 1 with a variable x. So we write now, for the first product, the number 1 is now replaced by y plus y bar. For the second product, the number 1 is replaced by x plus x bar. This idea is coming from the unit property that says x plus x bar equals 1. And from here, we're going to distribute this x bar to each of the variables y plus y bar. The same is true with the second product. The y here is to be distributed to x and then to the x bar. So x bar y plus x bar y bar plus xy plus x bar y. We have now 4 products here. Please observe that our first product x bar y is the same with the fourth product x bar y. According to our idempotent property, we can combine this x bar y and x bar y here into itself. So we write here x bar y plus this product we will copy here along with this product. This idea is coming from idempotent law that says x plus x equals x. Now we have 3 products and this is the sum of products. This is our final answer. Example 2. Find the sum of products expansion of the function f of x, y, z equals x plus y, and this quantity is multiplied to z bar. Our goal is to convert the function into a sum of products of the variables or its complements using identities. Let us write this function down here and then let us multiply the z bar to each of the variable inside the grouping symbol. So we have x times z bar plus y times z bar. We followed the distributive law. And from here, we're going to show that each of this product has another factor, which is the number 1. So we have now x z bar times 1 plus y z bar times 1. This is according to identity law, that x times 1 equals x. We have now 2 products here. In our first product, there is no variable y. In the second product, there is no variable x. That's why, for the first product, we're going to introduce an expression to replace number 1. And the expression contains y variable. So we have the y plus y bar. In the second product, since there is no x variable, we're going to replace this number 1 by an expression with x variable, and that is the x plus x bar. We get this idea from the unit property that says x plus x bar equals 1. And from here, let us multiply this product outside to each term of the grouping symbols. The same is true with the second product. So we have now x, y, z bar plus x, y bar, z bar. For the second product here, it becomes x, y, z bar plus x bar, y, z bar. We have now 4 products. Please observe that the first product and the third product here are the same. So we can rewrite this line by combining this x, y, z bar into itself. So we write now x, y, z bar plus x, y bar, z bar plus x bar, y, z bar. That is according to idempotent law. X plus x equals x. So we have now 3 sums of products here. This is our final answer. I hope you learned something from this video. See you again next time.